Okay, we're going to study the the energy it takes to change the state of water. That's like when you melt water or freeze water, or when you vaporize water, or when you condense water. But let's review a little bit. We have what's called thermal energy. And thermal energy is pretty easy to understand. If you have a series of molecules, and let's just make it like a nice ice crystal. Now, one thing that water molecules do when they're in an ice crystal, and I don't think they're actually laid out in a grid like this, but this is close enough. The atoms or the molecules of water, the H2O molecules in ice, are actually gripping onto each other. They hold each other in place. Now, we show these with little, I'll just show them like a grid like this. I think the structure is actually kind of complicated to draw, so let's just keep it simple. They hold on to each other with what are called bonds, molecular bonds. And think of them as like light little springs that are attaching them together. So these represent little springs. Of course, they aren't really springs, okay? This is just to help us understand, to imagine what's happening. So little springs between each of the atoms, or of the molecules of water, H2O, and they're vibrating. Like this molecule right here is moving around. But it's sort of held at this average location right here. It's held there by the bonds that it has with the other atoms, the other water molecules. So now if you add heat, let's say you have a really cold chunk of ice, and you put it on a beaker or something, and that beaker is hooked up to a source of heat, or maybe it's just left in a room temperature room. What will happen is that heat energy, which we call Q, will enter. Now what it is, it's other like air molecules or something that are moving around that hit the crystal and make the objects vibrate a little faster. Now, if you imagine this guy moving around in here, there's energy contained. There's the energy of motion, which we call kinetic energy. And that's the kinetic energy of the individual molecule. And also, when it squeezes in too close to another molecule, that other molecule wants to push it away. So there's energy stored in that, potential energy stored in that. So there's kinetic energy and potential energy stored in the position of these objects, or of these molecules, as they vibrate around. Now, if you add heat, they vibrate faster, or they squeeze in closer together, which adds to their potential energy or their kinetic energy. If you add up all the kinetic and potential energy that these molecules have because of their vibrational motion within the material, that's called thermal energy. Now, the way you usually experience thermal energy is by temperature. If we stick a thermometer in here, now this thermometer, this is not drawn to scale, okay? You stick a thermometer in, the thermometer gives you an idea of how fast these things are vibrating. So temperature is not the same thing as thermal energy, but temperature gives you an idea of how much thermal energy is available in the material. It also depends on how much material. Now, usually what we said, now what we did last time, when we talk about heat, when we heat water, we'll say, well, what does adding heat to these molecules do? Well, it changes their temperature, right? You get a delta T, a change in temperature. Now, how much heat you need depends on the mass. I mean, the more ice you have, the more heat it's going to absorb to melt it. Well, or I'm sorry, to raise its temperature. We're going to get to melting in a minute. Now, how much energy it takes to raise the temperature of a certain mass of ice or whatever depends on its its specific heat capacity. Okay, and so if this is a big chunk of ice, and maybe that ice is like at negative 20 degrees Celsius or something, it's in like a deep freeze, then it's going to take energy to raise its temperature. And so if I add heat to it, that's what it's going to do. Now I'm looking up right now the specific heat of ice. And it is, well, here's a nice little data table of different substances that shows the specific heat. Zoom in. And this is from our physics book. But aluminum, brass, carbon, copper, all these different materials. But ice has a specific heat of 2060 joules per kilogram degree Kelvin, or degree Celsius. So for ice, C equals 2060 joules per kilogram degree Celsius. Oops. Zoom back out. So if you have a kilogram of ice, which is like a liter bottle, if you take a liter bottle, you freeze it, and it's below 0 degrees Celsius, and you want to raise its temperature or whatever, for each increase in temperature of just 1 degree Celsius for 1 kilogram, it takes 2,000 joules of heat energy absorbed from the environment to do that. So it takes a lot of energy to raise the temperature of ice. And this is kind of what we did before. We did it for, this is for ice. Now for water, the specific heat is even bigger. It's 4,180 joules per kilogram degree Celsius. So it takes over twice as much energy to raise the temperature of liquid water as it does to raise the temperature of ice. But of course, there is a maximum temperature at which ice can reach before the bonds start breaking. And this is what we call changing state. When you change the state of something, you go from a solid to a liquid. Now, if you go from a solid to a liquid, we call that melting. If you go from a liquid to a solid, we call that freezing. But the only difference between freezing and melting is that when you're melting, it's absorbing heat from the environment. When it's freezing, it's releasing heat to the environment. The water is. And then, of course, we have from liquid. So anyway, this is from solid to liquid is melting. From liquid to solid is freezing. Then you have a liquid that it can evaporate, or it can you can boil it away, and that's from a liquid to a vapor or a gas. But we call it water vapor. When water is in a gaseous form, we call that vapor or water vapor. So if you go from a liquid to a water vapor, of course, we call that boiling. And when you go from a vapor to a liquid, that's called condensing. And you might have heard of like a condenser or something like that in a refrigerator. That's what it's doing. It's taking a gas and turning it back into a liquid. Now we're going to study this for water, but a lot of materials will do this. You can have a change of state. like this. There is, by the way, when you go from a solid back and forth to a gas or a vapor, and that's called sublimation. We're not really going to study that. Water doesn't do that at atmospheric pressure. I mean, here, the nice thing about where we're at living on Earth is that we're at a pressure where water can exist as a solid, liquid, and a gas, all at the same time. That's pretty unusual. If you're way out on a comet, way out in space, it's so cold that water can only exist as a solid or a gas. The water can sublimate, go directly from a solid to a gas. That happens in a vacuum. But that's not really necessary for what we're going to be studying. So let's talk about this change from a solid to a liquid. What's going on? So if you had a magical microscope and you could look at a little tiny, let's just look at a little tiny water or an ice crystal. And again, it doesn't have this particular form, but this is just easier to draw. So these guys are connected to each other through bonds. Now they're wiggling, they're all vibrating, they have thermal energy. The more thermal energy they have, the higher the temperature, until you reach a temperature where if you add any more heat to it, like from a hot plate or something like that, or just heat from the environment. Like this could be an ice cube in your drink. And why do we put ice cubes in drinks? Okay, see, I usually go to Taco Bell. I usually get I always get a Diet Pepsi because then I can pretend like I'm trying to. I don't like sugar drinks anymore. I just can't drink them. So here's some ice cubes floating in water. By the way, the fact that water is less dense when it's a solid than when it's a liquid, very unusual, and very lucky for us that ice floats. Now, you know that, okay, this is at 0 degrees Celsius, and room temperature is about 25 degrees Celsius. So we know that heat flows from high to low temperature. So heat's going to flow in here. Heat's going to flow into the ice, but into the ice water. But one thing we'll notice is that the temperature does not increase. If you put a thermometer in your Diet Pepsi, it's about 0 degrees Celsius, and it'll stay 0 degrees Celsius, or very, very close to 0 degrees Celsius. But what's the price we pay? Even though we're adding heat, heat is flowing into it from the environment. The ice, well, what happens is the ice melts, and so our drink gets watered down. But at least it's still cold. Okay, and so anyway, so what's happening is that as heat is added to our system from the environment, instead of making the atoms jiggle faster, it breaks the bonds apart. And that takes work to do. So this heat, maybe a water molecule or an air molecule, will hit the side of the glass and transfer its energy into the ice water, and then the liquid water hits the ice cube, and so something hits this and it knocks it away. So it breaks these bonds. And then what happens is that you'll have a very disorganized, when all the ice is melted, these water molecules, they stick together. They're still kind of bonded together, but they are free to just slip around and move. They're moving so fast that they can't arrange themselves into a crystal because they just have too much thermal energy. They're just jumping around too much to form bonds between them, but they still kind of stick together. And that's what a liquid is. So it takes a certain amount of heat to break all the bonds and turn a solid into a liquid, to melt. Okay? And, you're doing the same thing to aluminum, Timothy. You have to get the aluminum metal up to, a certain temperature before the bonds between the metals start to break apart, and then it melts the aluminum, turns it into a liquid. And so, now, what we have found is that it takes a certain amount of heat to melt a certain amount of ice. Now, the amount of heat you need is directly dependent on the mass. M is mass. But remember, there's no temperature change here. Remember, we had Q equals mc delta T. That was the heat needed to raise the temperature of the water. But here, we're not going to raise the temperature of the water. We're just going to break the ice apart. So what we need is, it's called H sub F. It's got a really screwy name. It's called the heat of fusion. And it's the amount of heat needed to melt a certain mass of ice. Okay? So the way you find it is, if you measure the heat of fusion, it's the heat needed to melt a certain mass of ice. This is M stands for mass. And so this has units of joules per kilogram, or joules per gram, or depending on whatever units you're using for energy and for mass. Now for ice, and again here I have my physics textbook has a table for heat of fusion. So here's water, but ice, the transition from water to ice or ice to water. Look how much energy it takes. 3.34 times 10 to the 5 joules of energy to melt 1 kilogram of ice. That's a lot of energy. It takes a huge amount of energy to melt ice. Or you have to release a huge amount of energy to freeze. So ice, from ice to water, oh, thank you. No, just, you don't have to be too polite. Let's see. Okay. Ice to water has a heat of fusion of 3.34 times 10 to the 5 joules of energy per kilogram of mass. Now that's 10 to the 5, what is that? That's 33,400 joules of energy to melt 1 kilogram of ice. Okay, and actually, I mean, if you look at all these substances, and I'm not going to zoom back in again, let me just hold the book up. Look at all these substances, and there's more, like aluminum. You could look it up for aluminum. But you have copper, mercury, gold, methanol, iron, silver, lead, and water. And, well, copper's pretty good. 2 times 10 to the 5, it absorbs a lot. The problem is to melt copper, you got to get it to really high temperature. But look at the 10 to the 4, 10 to the 4, 10 to the 5, 10 to the 5, 10 to the 4. Look at water. Water's the highest of them all. Water has the highest heat of fusion of everything listed here. And we use that. We take advantage of that. So here is the heat of fusion for water. This is the amount of energy it takes to melt a kilogram of ice into water. Now, it also takes energy, once you have a liquid, so here are the water molecules. They're still sticking together. They're really close together. In fact, they're closer together when they're a liquid than they are when they're a solid. And that's just because of the way water arranges itself into crystals. But these guys are moving really, really fast. And if you keep adding heat, their temperature will go up because they're going to move even faster. Their thermal energy will go up until they can't move any faster without just taking off and breaking all the bonds, all the connection they have with the other water molecules. And so they'll just take off. As you give them more heat, the water molecules will vaporize, turn into a gas. Now, what a solid is a neat arrangement of the molecules. They are not free to move around each other. They have to stay in place. They can jiggle, but they stay where they are overall. Water, if you follow the path of one water molecule, it's free to move all around. But they're still stuck together. This would be like a little water droplet. They're still kind of contained within a certain volume. But if you add heat, you start boiling the water, now all of a sudden they all take off. And so if this is my container right here, here's my beaker and here's all my water molecules, they will take off and fill the room. But they're really, really far apart now. The water molecules are really, really far apart. They're in a gaseous state. They're a vapor. It's a water vapor. Now if you put a thermometer in here and measure the temperature of this, the temperature will go up and up and up and up, and water will evaporate while you're doing that. But when you reach a certain temperature, it'll start to boil, that's when you get the big gas bubbles at the bottom, and it comes up and pops and goes out into the world. You're boiling the water. And that happens at the boiling point, 100 degrees Celsius. Right? Water melts at 0 degrees Celsius, but it boils at 100 degrees Celsius. That's how the Celsius scale was defined. And it takes energy to do that. How much energy? Well, Q equals the mass times the heat of vaporization. So this right here is the heat of vaporization. And if you look it up for water, the heat of vaporization, that is the amount of heat it takes to boil away 1 kilogram of water, is 2.26 times 10 to the 6 joules per kilogram. Hey, boiling water takes a huge amount of energy. And it happens at 0 degrees Celsius. If you have a fire, like your house is burning down, this is one reason we use water to put out fires. Well, we have a lot of it. But what happens is that when you throw water on a flame, if it vaporizes that water, it takes so much heat energy to do that, it actually lowers the temperature to 100 degrees Celsius, and wood will not combust with oxygen at that low temperature. I mean, 100 degrees Celsius is hot for us, but nothing burns. I mean, wood, paper, doesn't burn at that low temperature. So really the way that when you put water on a fire, the reason the fire goes out is that the water absorbs so much heat from the fire that it lowers the temperature to the point where the fire won't burn anymore. Also, when you cook pasta or you boil beans, you put it in boiling water, the temperature won't go any higher than 100 degrees Celsius. Maybe a little bit higher, I guess, if you put salt in it. But and it keeps the food from burning. Right? Take a bunch of pasta, break it into little, and put it in a pot, but with no water, and then put it on high. What'll happen? You'll burn the pasta. But you put it in water. The water, as it boils away, it keeps the temperature down. It also rehydrates the pasta and so on like that. But this is the heat of, this is how much energy it takes to vaporize water. So, here are the three heat equations that I want you to know. And one of you, we do this in physics as well, so this is kind of a repeat of what we're doing in physics. Q equals mc delta T. This is the heat needed to raise the temperature. C is the specific heat. C is equal to 4,180 joules per kilogram degrees Celsius for water. We're only going to deal with water in this class. Then you have Q equals m H sub F, or the heat of fusion. Heat needed to melt. And the heat of fusion for water, we said, was 3.34 times 10 to the 5 joules per kilogram. Q equals mH, now this is for water, HV, heat needed to boil or to turn a liquid into a gas. So the heat of vaporization here is 2.26 times 10 to the 6 joules per kilogram. Oh, one other thing, the specific heat of the water, of ice. What did we say it was? 2060, that's right. Okay. So, we can use this to figure out how much heat is needed to make certain changes. Now, one of the things this school uses is we use ice to keep our school cool during the hot days. And so right now, the cooling system is turned on for our school. So now, by the way, the building we're in is not part of the school's regular HVAC system. This building has its own independent heating, ventilation, and air conditioning system. But the rest of the school, what they do is during the middle of the night when electricity is cheap, we use these giant refrigerator things to freeze water. And then during the day, they use water to circulating through all the classrooms to absorb the heat in the classrooms, thus making the classrooms cooler, and dump the heat to melt the ice. And it's a very, very efficient, very cheap way to go. Let's suppose you have, let's do a problem. Given you have a mass of 3 kilograms of ice. Find the heat at 0 degrees Celsius. So the ice is at the melting point. The ice is ready to start melting. Q needed to raise the temperature to 25 degrees Celsius. So So how much energy is it are we going to absorb from the environment? Now, to do that. Now, and this is what we would use like in a ice chest. So let's suppose you've got a bunch of picnic stuff, you got some sandwiches and drinks or whatever, and you want to keep them cold. So you put in 3 kilograms of ice. That's about 6 pounds, 6 to 7 pounds of ice. Okay, how much heat will it absorb before it gets up to room temperature? Well, what do you have to do? You have this chunk of ice. Let's put the chunk of ice in some container. So here's your block of ice. Now it's at 0 degrees Celsius, so it's going to start melting. So as you put heat in, what's the first thing that's going to happen to the ice? Is the temperature going to go up at first? No, because what does the ice have to do? It has to melt. So you first have to add heat, and that's going to be m times h sub f. The mass of water times the heat of fusion for ice. Then what are we going to do? Once all the ice is melted and we just have this liquid, then it's going to absorb energy by raising the temperature of the ice. So you have to figure out how much heat was added by melting and how much heat was added by raising the temperature. And then you add those two together. So this is 3 kilograms. And what's the heat of fusion? Then we have to raise the temperature. That's mc delta T. And what is delta T for the ice? Well, it's going to go from 0 degrees Celsius to 25. So 25 minus 0 is 25. So this is going to be equal to, well, let's see, 3 times 3.34 times 10 to the 5 equals, that's going to be 1 million. Or 1.002 times 10 to the 6 joules plus, well, let's see, 3 times 4180 times 25 equals, and that's going to be 0.314 times 10 to the 6 joules. Now look what I did here, just to keep it on my calculator. It said 3.135 times 10 to the 5. So I just moved the decimal to the left one time to make it times 10 to the 6, and then I can just add these together. Let me check that. That seems low to me. Oh yeah, that's right. So 1.314 times 10 to the 6 joules. So we'll work a bunch of these problems on Thursday. Oh, you have your notebooks? You want to turn them in today, or you can turn them in on Thursday. Huh? Video? Oh, thank you. Thank you.